So Elena, yeah, I think that now you have started recording it. Yep. Okay. Thanks. So hi again. Well, this is the seminar number 17, and today we have as a guest we have Nerea Piñeiro from the University of Vigo. And as a very, very brief introduction, Nerea did her PhD at the University of Santiago de Compostela, and she's specialized in biochemistry of maritime soils. And for the last couple of years, she has been working developing an R package. And today she will briefly explain how it is structured, the main functions, and then also she will give us like a short tutorial on how it works. So yeah, I think that's all. Elena, if you want to add something, go ahead, and if not, yeah, you can start with the seminar. Thanks a lot.
Okay, so I guess I should begin. Thank you, Julian, for the introduction, and to all of you for organizing this workshop, and those that are here to listen to me today. I will try to make this brief. So I will share my screen now so you can see the presentation. Just 1 second. Okay, so you can see the presentation, right?
Yes.
Okay, thank you. So this library, as Julian said, I have been working on this for a couple of years already with several co-authors that are here today. The functions that we develop are the results of several years of working with BlueCarbon data. And the idea of the library is that as BlueCarbon estimations are fairly homogeneous, it's like people that work in this field use the same kind of estimations repeatedly. It was to try to standardize them and to automatize them so we will have this process much quicker and much easy to follow. So let's begin. So BlueCarbon ecosystems, as I guess many of you will know, are coastal ecosystems that accumulate organic carbon, either as biomass or in their soils as organic matter. Those ecosystems are depositional environments. What I mean with depositional environments is that they promote sedimentation, usually because of the presence of marine plants, either mangroves or seagrasses or saltmarsh plants. And this sedimentation ends in an accretion. So the sediment will increase in height, and this will vary organic matter, okay, and also inorganic matter. This will represent a chronological accumulation where deeper equals older and the upper part of the soil equals to younger. This will allow us to estimate sequestration rates, either for organic matter or heavy metals or pollutants or whatever, right? Because we have a chronological deposition. This is not exclusive of coastal environments, okay? It's also found typically in inland peat bogs. So we could use also this library and the functions from this library to estimate stocks and sequestration rates in peat bogs. So if we talk about BlueCarbon research, as I said, the main methodology is fairly homogeneous, mainly because of the work done by the BlueCarbon Initiative that released a manual in 2014, okay, where we can see how these ecosystems are sampled and what we do with these samples afterwards, okay?
Nerea,
the sampling is...
Nerea, sorry. ¿Le puedes dar a ocultar ahí en Teams?
Yeah.
Sí. Thanks.
Yeah. Okay. So usually what we do is to take cores from the soil, okay? And then we will subsample those cores to get samples. We won't analyze all of the samples, but a representative number of them. This has the main problem of this is that we can get many different data sets where the sampling process was different. And with different, I mean, we have collected a different number of samples per core, or the size of the samples is different, etc. Okay, so we will get many different inputs as our data set. Okay, after this, we will analyze those samples in the laboratory. And here, what we will do is usually the same kind of analysis, where we will get the dry bulk density, organic matter content, organic carbon content, etc. And from there, we will go to the mathematical estimation. And finally, we will get the organic carbon stocks and sequestration rates. Okay. So this library, what it intends to do is to try to automatize these estimations. Okay. And for that, we try to collect all kind of data from laboratory with all kind of subsampling and make robust functions that can work with different types of samples as input, and it will always provide the same result, this organic carbon stock and sequestration rates. So the library has three main types of functions, okay? We will have a first type of function, which is functions to deal with core compaction. I will explain core compaction in a few minutes. Then we will have a second type of functions to deal with the data from the laboratory to transform it to be able to estimate stocks and sequestration rates later on. And we will have the estimation of stocks and sequestration rate properly as the third type of functions. Okay. So the first type, dealing with core compaction, we will have two main functions. The first one is to estimate the percentage of compaction of our core, and the second one is to decompact mathematically the core, so we will get the decompacted depth of our samples. In the transforming data type of functions, we have two functions as well. The first one is to estimate the thickness of the sample. I will explain this better when we get there. And the second one is to transform organic carbon to transform organic matter values into organic carbon values. Okay. Then in the stock and sequestration rate estimation, we have three main functions. The first one is to estimate the stocks. The third one is to estimate the sequestration rate. And in the middle of the two, you can see that we have an additional function that is called text extrapolation. This function, what it does is to give us an idea of, to explain this better. Many times we want to estimate the stock of our soil until 1 meter depth, for example, or until 15 meters depth, or whatever is the depth we are using for the standard. However, our core might not reach this depth. So what we will do, is to use some kind of function to predict what the stock will be at that depth. What the second function you see here does, this one, is to try to give us an idea of the error we will introduce using this kind of extrapolation. Again, I will explain all of the function one per one, so you will see this better. So the first two functions are for dealing with core compaction. Okay, when we collect samples with cores, usually as we use percussion, manual percussion, there is going to be a compression of the sediment inside the core. Okay, so here we have a representation of a PVC tube into the soil. And we see there is no compaction, but in this one, there was a compaction of the sediment inside the tube. So what we have is a difference between the real surface of the soil and the surface we can see within the PVC tube. So the first function, what it's going to do is to estimate the percentage of compaction from three main variables. The first variable is the external distance, the difference between the real surface of the soil and the top of the PVC tube. The internal distance, which is the difference between the surface of the sampling of the sample and the top of the tube, and the length of the tube is the third. Okay, So with these three variables, we will be able to estimate core compaction. And for that, we will use this function, okay? So with the field measurements, using the core estimate compaction function, we will obtain the percentage of compaction. And this is going to be done with a function that, with an equation that we can find in the BlueCarbon Initiative manual published in 2014, okay? And once we have this percentage of compaction, we can estimate the real depth of our subsamples. So we will have the percentage of compaction and the subsamples depth measured at the lab, and use this function, the function decompact, to obtain the corrected subsample depth. So if we see here the depth of the subsamples we took from the core, we will obtain the estimated real depth of those samples, okay? And those are the two functions we have to deal with core compaction. And also, if we have dry bulk density estimated in the laboratory, this function will be able to also correct dry bulk density, okay? Because it's a linear correlation between the two. The second type of functions that we will be able to find in the library is sample thickness estimation and organic carbon and organic matter transformation. So what do I mean by sample thickness? As I said before, when we collect cores, we won't usually analyze all the samples from one core, because this will increase the expenses in the lab. So what we will usually do is to collect several samples that we think will be representative of the core and analyze them, okay? So usually we will collect more samples in the surface of the core, because we know that organic carbon content in the soil change faster in the upper part, and then fewer samples in the bottom of the core. However, to estimate the carbon stock, we need to know the percentage of carbon of both our samples and the intermediate parts between the samples, okay? So what we do here, or what the library is going to do, is to divide this intermediate section between the upper and the lower subsample. So this part will be assigned the percentage of carbon and the dry bulk density of this sample, and this part is going to be assigned the percentage of carbon and dry bulk density of this sample. Okay, because we assume that those samples are representative of the whole core. And what we are going to do is to use the lower depth of the sample and the upper depth of the next sample to estimate the middle point. There is a different way to do this that I have seen published, which is to use the middle part of the sample to estimate the middle part of the section, and then divide this section between the upper sample and the lower sample. The problem with this is that if the two subsamples have a different size, then the middle point won't be in the middle of the section. This is not a problem in many of the studies where I have seen this, because all the subsamples have the same thickness. But this is not always the case. So to avoid having this problem, what the library is going to do is to use this method. And in this case, we will always know that the middle part of the sample is in the middle part, okay? So having the corrected subsample depth that we obtained from the decompact function, we will be able to estimate sample thickness by dividing these middle sections among the different samples. Okay, so we will obtain the thickness of the samples covering the whole core. Okay, this is a main function of the library that you can use to get this, but usually no. But it is already incorporated in the estimate organic carbon and the estimate sequestration rate function, so you don't have to use it before. But we wanted to give you the opportunity to use it separately, just in case you wanted to know the thickness of the samples. The second function from the transforming data type of functions is to transform organic matter into organic carbon. So estimate organic matter in the lab is much cheaper than estimated organic carbon. So there is a lot of articles or a lot of studies where you will only measure organic carbon in a few samples and then use the percentage of organic matter to transform and estimate the percentage of organic carbon in the rest of the samples, because we know that there is a very clear linear correlation between organic carbon and organic matter. So this plot here is the plot for Kurian 2012, which is a very famous study where he found a correlation between organic carbon and organic matter for seagrass soils. Okay, but this is a global correlation, but we know that depending on environmental variables and the quality of organic matter in the soil, this correlation might change. So usually it is recommended to have one function or one correlation for each sampling station, because if you are going to take samples in different areas, even if it's the same ecosystem, this relation between organic carbon and organic matter might change. However, if it is not possible to make a correlation, to estimate a correlation for all the sampling stations, the next recommendation is to do it by dominant species. This means that if you have a mangrove forest from a particular species, you will have a correlation for that mangrove forest. If you have a Posidonia oceanica meadow, you will have a correlation for that Posidonia oceanica meadow. If you have a Cymodocea or a Stostera, etc., you will try to have a correlation for each species. If this is not possible, then we will try to estimate a correlation for that ecosystem. And this is what the next function does. Okay, the next function is estimate organic carbon, and from an input of organic matter values and organic carbon values, it will estimate different correlations for a sampling station, the main species, and ecosystem. Okay, so it will fit different models and then provide an organic carbon value for each of your organic matter values. And how is going to do this? First, if you already have an organic carbon value for that sample, it will keep that value. If not, it will use the linear correlation estimated for that sampling station to give you the value. If there is no linear correlation estimated for that sampling station because you didn't have any data about organic carbon, or because the correlation was very poor, then it will use the correlation for that dominant species. If you don't have this correlation, then it will go for ecosystem. And if for any reason, like you didn't provide any organic carbon data, or the correlation were very poor, or the number of samples was very low, it will use published equations to estimate this organic carbon value. So what the function does is to always provide an organic carbon value for each organic matter value. Okay, we will see after when we do the tutorial how this works. And last, we have the functions that are used to estimate organic carbon stocks and sequestration rates per se. So now that we have all the samples from our core, what the estimate organic carbon stocks function is going to do is to set a depth, okay, 1 meter by default, but you can change this depth in the equation to provide you with a stock, okay? So what it will do is to estimate the organic carbon mass of the first sample and just add the organic carbon mass of the following samples until it reaches the water depth. In this case, it will add the organic carbon mass from sample 1, 2, 3, 4, and 5. And then a sample 6 is half of it within our depth and half of it below. What it will do will be to divide the mass of organic carbon in sample 6 by its thickness, and multiply by the thickness that is within the depth that we want to estimate. And this is the carbon stock. However, as we said before, many times we want to estimate the carbon stock until one depth, but our core is shorter. So in this case, what the same function is going to do, it will realize that the core is not long enough, and it will estimate a correlation between depth and accumulated organic carbon mass, and then predict the accumulated organic carbon mass at the desired depth. So it will always provide us with a stock. What do we need for this function? We need the corrected subsample depth that we already obtained with the other functions, the corrected dry bulk density, organic carbon percentage, and the desired depth. That, as I said, if you don't say anything to the function, it's going to be 100. If your samples are in centimeters, then it's going to be 100 centimeters, 1 meter. And we will get a stock for each core. As I said, it will be the accumulated organic carbon mass until that depth of the predicted organic carbon mass if the core was shorter. So, as I said before, we have a function that the idea is to give us an idea of how good was our prediction for the cores that were shorter than the depth that we wanted. This function doesn't estimate the error of this prediction, but what it does is from your data set of cores, it will extract all the cores that do reach that depth and estimate the real stock at 1 meter. Then it will divide those cores by the 25% of their length. If it is 1 meter, it will be 25 centimeters, and estimate the prediction using only that length. It will do the same for the 50 first centimeters, 75, and 90, okay? And then it will provide these two plots. These two plots is going to compare the real stock with those predictions. So if you see here in the right, the red dots are the prediction of with the 25 first centimeters. The green dots are the 50, the blue ones 75, and the purple 90. If those dots are on top of this line, it means that the prediction is exactly the real stock estimated with the whole core. If those are above, it means that it overestimated the stock. And if they are below, it means that underestimated the stock, okay? And in the left, we have the percentage of error between the predictions and the real stock. So we can see that the percentage of error over the total stock at 90, using the 90 centimeters to predict is much lower than using 25, which makes sense. So this function is just so you can have kind of an idea of what kind of error you might be having when you use extrapolated stocks instead of the real ones. And last, the sequestration rate function. What it will do is, if you provide the age of the samples with depth that you might get from radiocarbon dating or lead-210 dating, it will estimate the accumulated organic carbon stock of the time frame you give to it. By default, it's going to be 100 years, but again, you can change this very easily. And then divide by the number of years. So you will have the average organic carbon sequestration rate in the last, by default, 100 years. So what do you need for this function? As for organic carbon stock, you are going to need the corrected subsample depth, the dry bulk density, the percentage of organic carbon, the sample age, in this case, and the time frame you want to use to standardize. and you will get an average sequestration rate for each core, okay, which is going to be the accumulated organic carbon mass by time. Okay, how can I stop sharing? Okay. Does anybody has any question until here? No? Okay. So what I have prepared now is the code for the tutorial of the library. So I can go over it and you can see how we are going to use the functions and what the results are and what the warnings can be when we are using the library. So this, one moment, please. I will share the screen with you again. So this library you can find in this web page. And in the web page here in articles, well, you will have an explanation of what I just said, what every function does. And in articles, you have the tutorial, okay? So it will explain you how to load the example data and how to use the functions in R to estimate the stocks and sequestration rates with that data. So we are going to do this now using R. And what we are going to do is to estimate the organic carbon stock of the first 75 centimeters and 1 meter of the example core data, okay? And also the sequestration rates for the first 100 and 200 years. Okay. So first you will have to install the library. I have it already installed, so I'm not going to do that. We load the library. And if we use data, we can see the example data that is within R. And we can see that we have, from the BlueCarbon library, 2 example data frames. The first data frame is a data frame with soil cores, okay? And the second one is a data frame with field measurements to estimate core compression, compacting. So we are going to load both data frames, and we can take a look of the information in there. So in the core compaction data frame, we will have the ID of the cores, the sampler length, this means that the length of the tube, the internal distance, if you remember at the beginning, those are the measurements, okay? The sampler length, the internal distance, and the external distance. And using the estimate compaction function, we can get the percentage of compacting of each core. What the function is going to give us is the same data frame we use, okay, this one, with an extra column with the percentage of compaction of that core, okay? We can also see here that we got a warning, and this warning is telling us that there was a core without data, and that it has removed it from the final data frame. If we go here and look at that core, we can see that, yes, it didn't have any data, and that's why it removed it, okay? But the function is going to give you the percentage of compaction for all the cores that have data. But if there is any core without data, it's going to let you know that it has removed that core. So you can just go back and check why you have missing data, okay? Here in the function that we use to estimate the core compaction, the first field is the data frame with the data, and then the other is the name of the columns. So you can see that the column core, the name is core, we have here, sampler length, internal distance, external distance. Those are the same as the by default names. But imagine that you have a data frame with different column names. You can just change here the name, and it's going to estimate the compaction anyway. And this is true for all the functions of this library. You can just change the name of the columns, or you can use always the default names, as you prefer. So once we have the percentage of compaction, if we go to this other dataset, example dataset, what we have is the ID of the core, the sampling site, which ecosystem it belongs to, which species it belongs to. We have the percentage of compaction already here, the minimum depth of the sample and the maximum depth. It means the top and bottom depth of that sample, dry bulk density, organic matter, if we have the organic carbon, if not, not. And if there is age, also the age of that sample. And we will have one core after the other. So you can see here, when we finish this here. So here, this is the last sample of core HG0101. And here it starts the next core. So we will have one core after the other. As we already know the compaction, we can use the function decompact to get the corrected sample depth and dry bulk density. So what we got here, BlueCarbon decompact, is the same data frame with 3 extra columns: the corrected minimum depth, corrected maximum depth, and corrected dry bulk density. Okay, and we can see them here. Okay. Also, we got a warning. And the warning said that there was several cores that didn't have any data for percentage of compaction. The function is going to assume that the compaction was 0. It means there was no compaction for these cores. But it will let you know, okay, that it set compaction to 0 for the following cores. So you can check again if this is correct. Okay, the next function is the functions to estimate organic carbon from organic matter. So if we run this function, okay, it takes a bit because this is quite a big function. We are going to obtain 3 things. The first thing is this plot, where we are going to see a plot of all of our samples, okay? The red ones is measured. This means that we already have organic carbon data for that sample. And then we are going to have samples that were estimated for several models. The green dots mean that it was estimated for a model of the whole ecosystem. The blue one, a model for that species. And then in this case, we have this purple one that means that it was estimated for a published equation for mangroves in this case. Okay, why? Because either we didn't have any data of organic carbon for mangroves in this example, or the model was very poor, okay? And also we got 2 warnings that let us know that although it did provide the organic carbon value, the samples of organic matter were above or below the range of the models. So it's just for you to know that the models for those samples might not be very good. So you can go and check. And the other 2 things that we are going to obtain is, first, a data frame with the original data frame and 3 additional columns, okay? The column of estimated organic carbon, ¿vale? Estimated organic carbon standard error for with that model, and also a column name origin that is going to let you know which model was used for that particular sample. And a third data frame, which is a data, it's not a data frame, it's an object, including all the models. So you can come here and look for the model that was used to estimate that sample and check the parameters of that model. Okay. If anyone has any question, please just interrupt me, because if not, I cannot see you. So I don't know if you are following or not. And finally, we have the functions to estimate stocks and sequestration rates, okay? So the function estimate stock, if we use the data frame that we just get from the estimate organic carbon, we are going to obtain a data frame with these columns. The first column is the name of the core. So for each core is going to provide stocks, a stock for the whole core, okay, and the maximum depth of that core. So the first core has a stock of 2.6 in 156 centimeters, and a stock for the depth that we ask. In this case, we have nothing here because the depth by default is 1 meter, okay? But in this line of code, we are going to estimate the same, but we are changing the depth from 1 meter to 75 centimeters. So we just run like this, and we obtain it the same, but in this case, the stock is for 75 centimeters. So again, we have the stock for the whole core, the maximum depth of that core, and then the stock at the depth that we just indicated. The last column is the standard error for the predicted stock in case that the core was not long enough to reach that depth. In this case, the core was 23 centimeters. So the stock at 75 centimeters was predicted. Okay, so it will give us the standard error. Okay, and I have told you that we have an additional function to try to estimate the error.
Nerea?
Yes.
Sorry, I think you have a question from Vera.
Yes,
Maybe?
sorry, can I make a question? What are the units that this results? Megagrams by hectare or?
So the units are the ones that you
the
give.
Organic carbon stock.
So organic carbon and organic matter are in percentage. That's important. Yes. But then the final units you will get are those that you provide the dry bulk density in. If your dry bulk density is in grams per square centimeter, sorry, square not, the other one,
cubic.
The one with the 3, sorry. Then that's how you are going to get your stock. In this case, my dry bulk density was in grams per centimeter, so the stock is going to be grams per square centimeter until 1 meter depth, or until 75 centimeters.
Okay, thank you.
Was that your question? Yeah, organic matter and organic carbon we have to provide always in percentage.
In percentage, yes.
Yes, but then the final...
the normal units,
the other unit you can provide whenever you, whatever unit you want, and then the stock is going to be in that unit.
Thank you.
And also, the default depth is 100. So if your the depth of your subsamples is in centimeters, then the default depth is going to be 1 meter. But if you are giving the depth of your samples in meters, for example, then the default depth is going to be 100 meters. So you have to take this into account as well. And you can do two things in this case. You can either transform the depth of your subsamples into centimeters, or you can just come here to the depth and let it know that you want 1 as the standard depth. So if you give your subsamples by meter and you change depth to 1, you will have 1 meter again.
Yeah. Thank you.
Okay. So I told you before that we have this function that will let you know more or less the error you are doing with your, when you are predicting the stocks. And it will use all the cores that reach your desired depth to estimate this error. And this is a test extrapolation. So if we run this function, we are going to get the kind of plot that I showed you before. Okay, so it collects all the cores that reach 1 meter and estimate the real stock, the observed stock, and then estimated the stock using only the first 25 centimeters, the first 50, and the first 75, and the first 90 centimeters to estimate the stock, and is comparing them, okay? And you have here the, as I said, above is an overestimation and below is an infraestimation, and you have here the percentage of error over the total stock. Okay. And last is the sequestration rate. So the sequestration rate works similar to the stock estimation. If we run this function, we are going to obtain a data frame with the name of each core, the average sequestration rate in the whole core, and the maximum age that the core reached, and then the sequestration rate for the time frame we provide. By default is 100 years, okay? But we can change it. For example, here, we will change the time frame to 200, so we will have the average sequestration rate for the last 200 years. Okay, and here it is. And we got a warning, which is that these two cores were younger than the time frame provided. That means that it were younger than 200 years, so it didn't estimate that sequestration rate. If we go here to see the whole thing, we see that we have these two cores where we didn't get an estimation for the sequestration rate at that time frame. We did get the estimation for the whole core, which in this case was 103 years old and 112 years old. But we see this core here, we didn't get a sequestration rate either, although it's not in the warning because it's not more than 25% younger. So the warning only works for the 25%. And that's it. Those are all the functions. As you can see, the sequestration rate data frames that we got, we only have 14 cores, although for the stocks, we have 78 cores. Why? Because we have 78 cores in our data set, but we only have age for 14 of them. So we don't need to tell the function which ones we want with sequestration rates. It will automatically just only select those with the ages. And that's it. I don't know if you have more questions.
Yeah, thanks, Nerea. It was a very nice presentation. Actually, I think it would be very helpful for the users, for the future users. And I don't know if anyone has any question. Meanwhile, yes. I have one, Nerea, but well, I can wait. I can wait. I think there might be some more important questions than mine.
Sorry.
I don't know who was asking. Yeah. Go ahead.
Probably we will be doubts when we are working with our data and with these clients. It will be possible to ask from you or to know how if you can help us, because now I think it is more or less easy, but I'm sure when I will do with my data, things normally don't work so nicely. So
yes, of course.
Okay, we can ask later our doubts, our issues in working with this program. We can ask you in that platform.
Yes, you have my information in the webpage. There is also a button to report any bugs that you might find with the code because it doesn't work properly or it doesn't work with your particular data. You don't hesitate to contact me, and I can help you make the functions work for your data.
Okay. And I want to give you congratulations because it's a lot of work in here.
Thank you. I'm very happy about it too.
Yeah. Thank you.
Nerea, can I ask you a question?
Yeah.
Yeah. Maybe you already said, but I wasn't sure how you decide which model to fit, because I see that you have this species model, then ecosystem model, but can the user decide that, or
No.
so
So there is
how
like
can you explain us how it works, please?
Yeah. So once you provide your data, the function is going to try to fit all the models. And then if there is more than 5 samples of both organic matter or organic carbon for one particular station, there is going to produce a model, and also for the ecosystem and the dominant species, etc. And then it will test, it will check the R square of its model, and if it is lower than 0.5, it's going to delete them. So it will only keep those models where you have more than 5 samples per model and then more than 0.5 R square. And once it has the good models, just to say, it will start with a correlation. Like if I have a model for that station, I'm going to use that one. If I don't have a model for that station, I will look for the dominant species. If I have that, I will use it. If I don't have neither of those, I will go for a model of the whole ecosystem. And just in case that it cannot get any model for that sample, then it will go to the published equations. But you will always get a value for each organic matter value. And then you will get 2 data frames. The first one, well, 2 objects, a data frame with the final values and a column where the model is indicated. And then you will have an object with all the models estimated by the function. So if you are not happy with the model that it gives you, you can go and extract the other model and rerun it. But automatically the function is going to give you a value and doesn't allow you to choose.
Thank you.
Yeah, also, if any of you have any recommendation or something that you would like the library to do, also write to me. I will take it into consideration. I won't implement it for this version, but maybe for next one.
But I think Vero has a question too. Vero, you are mute, I think.
Sorry, can you hear me now?
Yeah.
Hi, thanks for your talk, Nerea. In relation to this that you were saying, are you planning to extend the packets to terrestrial soils and similar methodologies?
I wasn't, but I think it will fit perfectly with Bitbox because those are also the positional environments. I don't see a problem to use the functions to estimate the stocks of terrestrial soils. The only thing is that if you do not have a function to estimate organic carbon from organic matter, it won't be able to use published equations because those are not implemented in the package. But I'm not sure what the function will do. Maybe it will break, or maybe it will just report in an empty value. We can try.
Okay. Yeah, I think it would be useful, but next versions.
Yeah, but if you already have like organic carbon or and organic matter values, they are more than 5 samples, I think it will be able to estimate a function for that species or that station, and then there shouldn't be a problem. Or if you already have the organic carbon data, just run the estimate stock function. Yeah, the only problem is with the organic carbon transformation. If not, the function just works with depth.
All right. Perfect.
I don't know if there are any other questions. If not, I think we can finish it here. Yeah. So thanks again, Nerea. Thanks everyone for joining today, and see you at the next seminar that hopefully would be in February.
Okay, bye-bye.
Bye.
Thank you.
Bye-bye.
Thank you. Bye.